Okay, in this segment we're going to be talking about a circuit called the differential pair, and in particular we're going to look at the MOS differential pair. And we're going to be looking at this qualitatively at first to try to develop an understanding of how it behaves, independent of inversion level and the quantitative details of the current voltage characteristics. But we have here a circuit made from 3 NMOS transistors. So 2 of them, and this is the actual differential pair here. We're going to call M1 and M2. And there'll be 2 currents, I1 and I2. And we're going to have an input V1 and input V2. And then we're going to have, from this common source node down here, we're going to have a transistor, a bias transistor, MB, whose gate voltage is VB, whose job in life, again, like in the source follower, is to sink a constant bias current IB. So this is the bias transistor. These are the diff pair transistors. And this node here, which we're going to call the voltage of V, is called the common source node. And here V1 and V2 are the inputs. I1 and I2, the currents flowing out of the drains, or into the drains rather, of M1 and M2 are the outputs. And sometimes we'll take the current I1 minus I2 as the output. So this is sometimes it'll be convenient to think of I1 and I2 separately as the outputs of the circuit, and sometimes it'll be convenient to think of the so-called differential output current. I1 minus I2 as the output. We're going to make some assumptions about these transistors, and they're our typical assumptions. So we're going to assume that the transistors are matched. Same temperature. And that they have an infinite early voltage, so the early effect is negligible. We're going to assume that the 2 drain voltages here, we could call them VO1 and VO2. VO1 and VO2 are held high enough above V, that's the common source node, to ensure M1 and M2 are saturated. And I mentioned before we want MB to act as a current source, current sink. which means that we want MB to be saturated. So obviously that implies that we need to have that V is greater than or equal to VDS sat. But eventually we're going to want to know something about the input voltages rather than this internal node V, to say something about the minimum allowable input voltages, kind of like we did for the source follower. So we're going to be, when we start to deal with the IB characteristics of this circuit quantitatively, we're going to basically make the assumption that MB is saturated, and then go back and think about under what conditions would that be consistent. Okay, so what do we know about this situation? Well, let's suppose. Well, actually, let's just first start out by asking what do we know about the situation. Well, we can apply Kirchhoff's current law down here at this common source node. All right, so KCL at node V tells us something. It tells us that I1, which is the drain current of M1, which also flows out of the source of M1, plus I2, the current flowing out of the source of M2, have to sum together to equal IB. So in the steady state, we have that IB, the bias current, is equal to I1 plus I2. Suppose V1 equals V2. What can we say? About I1 and I2. Well, if V1 equals V2, then these two transistors, M1 and M2, will have the same gate voltage. By the way they're connected, they also have the same source voltage. So they have the same gate voltage, they have the same source voltage, and of course the default assumption here, if we don't show the bulk terminal, is that they both have the same bulk voltage, which is ground for NMOS by default. And so the only thing that might be different in principle is the two drain voltages, right? But we have assumed that these transistors are guaranteed to be in saturation, and we've also assumed that the early effect is negligible. So because they have the same gate voltage, source voltage, and bulk voltage, we know that the two currents should be the same by virtue of the matching assumption and saturation assumption and the fact that the early effect is negligible. So we could say that I1 equals I2. Furthermore, because we know KCL, because we know that they sum to IB, we can take these two things that we know and combine them and find that I1 plus I2 is equal to IB. Well, if I1 equals I2, that implies that 2I1 equals 2I2 equals IB, because we can substitute I2 for I1 or I1 for I2, and so by dividing both sides of this sort of triple of equations here by 2, we know that I1 equals I2 equals half of IB. So we've figured out, just by virtue of the matching and the way these things are connected, that under the conditions that V1 equals V2, that this bias current IB will be split 50-50 by the two transistors. And so if we were to take I1 minus I2 as our output, we would find that I1 minus I2 is equal to 0 under these conditions. Okay, so that's interesting. Let's suppose we're in this balanced state where V1 and V2 are equal to each other. So let's assume V1 equals V2, and let's say we increase V1 by some little bit, let's say delta V1. What happens? Let's think our way through this. What happens when we increase the gate voltage of M1 by some small amount? Well, the gate voltage of an NMOS transistor, if we increase it, would increase I1. So this leads to an increase in I1. Say an increase in V1 leads to an increase in I1. Well, that increase in I1 means that more current is coming out of M1 than we had before. So we could say that I1 started out at half of IB because of what we just figured out down here. And so I1 has become slightly larger than half IB. I2 is still half IB because it hasn't gotten the memo yet that we've increased I1. So what happens? Well, we have more current than IB flowing onto common source node V. So I1 plus I2 is greater than IB. Well, we still have MB sinking IB from V, so we have an excess of current flowing onto the node. Well, what does that lead to? Well, that excess current has to go someplace. It doesn't go into MB. It has to go into the node capacitance. So it flows into parasitic capacitance of node V, which leads to a positive dV dt, which leads to an increase in V. So that excess current will go into raising the voltage here on the common source node V. But what effect does that have? Well, V is the drain of the bias transistor MB, but it's also the source of transistors M1 and M2. So we have to ask, what is an increase in V? What effect does that have on the currents that are flowing in these three transistors? Well, if MB is in saturation and it's ideal, so there's no early effect, then an increase in V will not increase IB very much, if at all. However, being the source of M1 and M2 means that the increase in V is going to pretty dramatically decrease I1 and I2. Right? So the source was the most effective terminal at changing the current, the saturation current of the MOS transistor. The gate has a kappa in front of it. The bulk has a 1 minus kappa in front of it. and the source has a 1 in front of it. And so the source is the most effective terminal at changing the saturation current. So it's going to turn down the current in both M1 and M2. So the question is, where is V going to stop? Where is dV dt going to be 0? Well, dV dt is going to be 0 when I1 plus I2 is equal to IB. So dV dt equals 0 when the new I1 plus I2 becomes IB. Again, so the sum transiently was above IB, and then the increase in the source voltage turns the current level in both transistors down until the sum reaches IB again, goes back down to IB. Well, we know that I1 increased above IB over 2, and I2 decreased starting at IB over 2. So we have basically I1 is going to be equal to half IB plus some delta I, and I2 is going to be equal to half IB minus that same delta I. Right? So the amount by which we increased the current in M1 has to equal the amount by which we decrease the current in I2. It's a zero-sum game. These two currents have to sum to a constant IB. So if we make an increase in one, that has to come at the expense of the other one. We have to have an equal and opposite decrease in I2. Okay? So what we've done by increasing V1 is to steer some bias current toward M1 and away from M2. We could also tell a very similar story about an increase in V2 relative to V1. So if we started out V1 equal to V2 and we increase, let's say, V2 by some delta V2, well, that increase in V2 will lead to an increase in I2 because that's the way MOS transistors work. It started out at half IB, it becomes larger than half IB. The sum of I1 plus I2 now exceeds the current being sunk by the bias transistor. We have more current flowing onto node V than was flowing out before. That leads to an increase in the voltage V, which pushes back on I1 and I2 until the sum I1 plus I2 is restored to IB. And the net effect of that would be that I2 would be increased by some delta I, and I1 would be decreased by that same delta I. And so we would have steered some current toward the I2 side. Well, we could imagine telling a story about decreasing V1 relative to V2. If we were to decrease V1 relative to V2, then we'd be turning M1 off a little bit. We'd decrease I1. The decrease in I1 means that there's now a deficit of current flowing in from above onto node V. A decrease in current would result in V falling because the current in MB is still IB, and so we have less than IB flowing on from above. We have IB flowing out from beneath, and so V will have to decrease. We'll have a negative dV dt, so V will decrease. Well, the source voltage decreasing in M1 and M2 has the effect of increasing the current I1 and I2 by some amount. And that increase in both I1 and I2 will continue until the sum I1 plus I2 is restored back to IB. When that happens, we wind up with a little bit less current than IB over 2 flowing in M1, and we have a little bit more current flowing in than IB over 2 flowing in M2. So by pushing V1 down relative to V2, we've steered some current away from M1 and toward M2. Okay? So that's how the circuit works. I want to think about this a little bit more from a slightly different point of view. So I'm going to erase some of this stuff. See if I can do this without damaging the picture too much. Okay, so there's a diff pair. And so let's suppose we start decreasing V2, right? So V1 and V2 are both some voltage. So let's say V1 equals V2, somewhere in the middle of the rails, high enough to make V above VDS sat, but below, far enough below VO1 and VO2 so that these two transistors are saturated. So all three transistors are saturated. So such that now let's suppose we start decreasing V2. Well, we already figured out what's going to happen if we start decreasing V2. That's going to start steering some of I2 toward I1. So they started out at half IB, and now by pushing V2 down, we're going to make I1 slightly bigger. We're going to make I2 slightly smaller. We're going to keep pushing V2 down. We're going to steer more current toward the I1 side. Question is, how much can I1 increase and I2 decrease? Well, I can keep pushing I2 down by making V2 go down further and further and further. Let's suppose that I make V2 equal to ground. I've decreased it so much that I've gotten all the way down to the ground rail. What do you think I2 is going to be? Well, if V2 is equal to 0, this transistor is going to be pretty much as off as we can make it. Right? Not only is the gate voltage at ground, but the source voltage is probably going to be above ground. It certainly can't be below ground because it can't go any lower than the source of MB, because the only thing that's pulling it down is MB. And when V goes to ground, IB goes to 0, and it's not pulling down anymore. So if V2 is equal to 0, we basically have I2 is going to be very, very small. It's going to be about 0. Compared to I1, it's going to be negligible. And so that means that I1 is going to have to be supplying all of IB, right? IB is coming from M1 and M2, and if M2 is basically as off as we can make it, then all of IB has to come from M1. And so I1 has to be IB. I1 can't be more than IB because these two transistors would then be in series. I mean, in fact, in this particular instance, M2 is kind of not even in the circuit, really. It's not really contributing to KCL at this node. M2 might as well not be in the circuit. And if M2 is not in the circuit, what we have here is a source follower. Right, now we didn't take the current flowing through the source follower transistor as the output. We took the common source, or what we're now calling the common source node, as the output. But we have some idea of what this circuit is doing in terms of the behavior of the common source node at this point. So if all of I1, or if all of IB is flowing in I1, then the circuit is basically a source follower with V1 as or M1 as the source follower transistor and V1 as the input. So V1 is controlling what V does. So we know that V, for instance, is going to be equal to kappa times V1 minus VB. So V1 will control the value that V takes on. And if V1 goes up, V will follow behind it by a certain amount. We know that the incremental gain from V1 to V is kappa. Well, if we imagine not that V2 is all the way down at ground here, but is just lower than V1, we can say something about the relative sizes of these two currents. Right? We know that the current voltage relationship, the saturation current voltage relationship of a MOS transistor, is a fairly steep expansive function. In weak inversion, it's an exponential. In moderate inversion, it's some funny log squared 1 plus e to the x over 2 function. And in strong inversion, it's a quadratic. It's parabolic. It's not quite as steep as it is in weak inversion and moderate inversion, but it's expansive. And so a small difference in V1 and V2 leads to a large difference in the actual currents because relative to each other, because they have the same source voltage. And so let's say in weak inversion, something like an 80 millivolt difference in the gate voltages will lead to a decade difference in these two currents. Right? It's kind of like the 60 millivolt per decade rule with a kappa involved. So if kappa were something like 3/4, then the 60 millivolt per decade rule turns into something like an 80 millivolt per decade rule. So I don't have to have V2 very much less than V1 in order for this idea that I2 is negligible compared to I1, and the circuit sort of reduces to a source follower, with M2 not really contributing very much. So a relatively small difference and this is, I should say, V1 greater than V2. So relatively small difference between V1 and V2, such that V1 greater than V2 leads to the conclusion I1 much greater than I2, and so M2 might as well not be there, and M1 acts like a source follower controlling node V. Well, we could of course say the same thing about the circuit in reverse, right? So the circuit is symmetric in V1 and V2, and so if we were to say start decreasing V1 until it was at ground, so if we make V2 larger than V1 by even a relatively small amount, we steer pretty much all of the current to the I2 side, and I2 becomes IB, I1 becomes close to 0. The circuit becomes something like a source follower with M2 controlling the node V, and M1 might as well not be in the picture. Okay? So that's some intuition about what's going on with the common source node V. It's kind of like we have two competing source followers that are vying for control over node V, and the one that is the larger voltage basically wins more of the bias current and gets to have greater control or exercise greater control over node V. So we're actually, believe it or not, in a position to sketch something about the IV relationships of this circuit. All right, so qualitative IV sketch here. So what we're going to do is we're going to plot here is the difference between V1 and V2, V1 minus V2 on the horizontal axis here. And on the vertical axis we're going to plot I1 and I2, I1 minus I2, and I1 plus I2. So I1 plus I2 is the easiest. Right, we know that that's a constant. Right, so that's basically it's I1 plus I2. And that's IB. This will be half of IB. Right there. And we know that I1 and I2, let's maybe put it here, half IB. We know that I1 and I2 are both half IB at this point. We figured out that V1, when V1 equals V2, which means V1 minus V2 is equal to 0, both of those currents pass through this point. We figured out then when V1 exceeds V2 by some amount, it's not very big necessarily, that I1 is practically all of IB. So this is I1. And I2 is practically 0. And we figured out that when V2 exceeds V1, that I2 will be practically all of IB. And I1 will be practically 0. All right, so that the sum of these two things is equal to IB. And so we know that here I2 has to start to decrease until we get to IB over 2, and then it has to continue decreasing until we get to 0. And so it's going to have to do something like that. We know that the sum of these two things is equal to a constant, and so we can basically subtract I2 from IB and get I1. And so we're going to have something that looks like this. And to get I1 minus I2, which was the differential output current, we basically have to subtract I2 from I1. And so where I2 is practically 0, we don't subtract anything from I1, and so I1 minus I2 is going to be looking like I1. When we're on this side, when I1 is practically 0, I2 is up here at IB, we're going to have something like minus IB. So if I make a minus IB down here, I1 minus I2 is going to be down here. We know that I1 minus I2 has to go through 0 at 0 because I1 minus I2 is 0 here. And so it's going to do something like this. Okay, qualitatively, that's what we sort of figured out, aside from exactly the details of how these sort of nonlinear curves behave, whether they're exactly symmetric or not or something like that. That's a detail that we're going to have to work out quantitatively. But we figured out that asymptotically, I1 and I2 have to switch from being all of IB to basically be 0, and they have to go through IB over 2 here in the middle. And therefore the difference has to switch from plus IB for positive V1 minus V2 to minus IB for negative V1 minus V2, and has to go through 0 at 0. Okay? So that's it for this segment. We'll pick it up here next time.